So okay, I'm repeating again. It's hydrodynamics, which is study of fluid in motion. We start hydrodynamics with the concept of viscosity. Viscosity is the property of fluid due to which one layer opposes the motion of another layer. It's a type of internal friction which act between the layers of the fluid. When I'm saying fluid, it's both liquid as well as gases. So if I draw different layers, this is the surface. This is the fixed surface. Huh? If I draw different layers of the fluid, say this is the first layer. I'm just drawing different layers here. This is the first layer. Then this is different color. This is next layer of the fluid. Then this is the next layer of the fluid. And so on. This layer has some velocity. Let's say that velocity is v1. This layer have a velocity v2. This layer have some velocity that is v3. So the layer which is in contact with the fixed surface have minimum velocity. This one have comparative higher velocity, and this have velocity higher than v2. So these velocities, if I go from bottom to top, these velocities are in increasing order. v3 is greater than v2, which is greater than v1. So these velocities are in increasing order when you go from bottom to the top there. So the frictional force which actually oppose the relative motion between the two layers is known as viscosity. So this layer will try to slow down this layer. This layer 2 will try to slow down this layer 3. So if layer 1 try to slow down layer 2, that means layer 1 is exerting a force, a frictional force on layer 2 in opposite direction. If layer 2 tries to slow down layer 3, then it will apply a force, viscous force in a direction opposite to that of velocity. This is the viscous force that we are going to study. We will study this viscous force. And the property due to which this viscous force comes into play is known as viscosity. So it's a type of friction. Now let's see on what factors does this viscous force depends. So Fv is viscous force between layers. Now this viscous force depends on first part. Viscous force is directly proportional to A, where A is area of layer. A is the area of each layer. So this viscous force depends upon the area of each layer. This viscous force depends upon dV over dx. See, what is dV over dx? I should draw two layers to explain this. So this is one layer. Sorry. And this is one layer. One thick layer. So the liquid molecules at the top of the layer and at the bottom of the layer have different velocities. So the bottom one, let's say the velocity of bottom one is v. The velocity of the top one is v plus dv. And the separation between them is, let's say, dx. So this dv is the change in velocity when you go from one layer to another. And dx is the separation between them. So we call dv over dx as velocity gradient. This is known as velocity gradient. Velocity gradient simply means change in velocity with respect to position. When you combine them, you can write this as that viscous force is proportional to A dV over dx. When you remove sign of this proportionality, you will get viscous forces, it's eta A dV over dx, which is eta A dV over dx. Here, this eta is known as coefficient of viscosity. This eta is known as coefficient of viscosity. You can even put a negative sign here. This negative sign will simply tells that the direction of viscous force is opposite to that of velocity. Negative sign tells that direction of viscous force is opposite to that of velocity. So viscous force will act in the direction opposite to that of the velocity of the layers. Means if layers are moving along positive x-axis, then viscous force will act towards the negative x-axis. Next thing, you can also calculate the value of this coefficient of viscosity, the unit of this coefficient of viscosity. Or I'm writing just one more thing. This coefficient of viscosity basically defines the effect of medium on viscous force. For different type of medium, like if you have water, then viscosity is different. Different mediums have different viscosity, just like density. Water have different density, air have different density. In the same way, viscosity of air is different, water is different. So different fluids have different coefficient of viscosity. It's just like density or refractive index. Different coefficient of viscosity. Now, if you want to calculate the unit of eta, so you can write that your force is its eta A dV over dx. So you can write that your eta is it's F by A dx by d. This is your eta, F by A dx by d. So force is Newton, area is meter square, dx is meter, velocity is meter per second. So if I write its unit, then this is Newton per meter square seconds is eta. SI unit of eta. Or you can just write this as Newton per meter square is pascals. So you can write this as Pascal second. This is the unit of eta. SI unit of eta is Pascal seconds. Or this can also be written as this Pascal second is also known as decapoise. This is the SI unit. You can write CGS unit of coefficient of viscosity. Its CGS unit is, you can directly write CGS unit from here. Instead of Newton, just write dyne. Instead of meter, just write centimeter per square seconds. That's the CGS unit. Or you can write this as decapoise, or poise is the CGS unit. This is the CGS unit of coefficient of viscosity. Sure. Next is the factors on which this viscosity depends. Viscosity, first it depends on nature of material. For different materials, the value of viscosity is different. Viscosity depends on nature of material and temperature. Depends on nature of material, temperature, temperature and pressure. The nature of material you understand. For different materials, the coefficient of viscosity is different. Now you have to see how it depends on temperature and pressure. So viscosity, I'm just discussing variation with temperature. Viscosity of liquid increase, I'm sorry, decrease with increase in temperature. Decrease with increase in temperature. So when you increase temperature, the viscosity of liquid will decrease. If you keep on increasing the temperature, viscosity keep on decreasing. While if you have the reason is very simple. When you increase temperature, the intermolecular forces decreases. And viscosity is due to intermolecular forces. Once the intermolecular force decreases, the viscosity decreases. But in gases, it increases with increase in temperature. Increase in temperature. The reason is in liquids, this viscosity is due to intermolecular force. But in gas, the viscosity is due to the motion, the relative motion of molecules. So that's why it changes. Next is, so we did these two things, it increase in temperature. The next is pressure. Viscosity of liquids increase with increase in pressure. If you increase pressure, then viscosity will increase with increase in pressure. Except water. Water have a very different behavior. If you take water, then viscosity will decrease. But viscosity of gases are absolutely independent of pressure. You keep on changing the pressure, viscosity of gas will not change. Viscosity of gas is independent of pressure. So if you change pressure, then viscosity of gas will not change. So you have a metal plate. This is a liquid film over the table. This is the liquid film. Over the liquid film, a box is placed. This is plate basically. It is connected to the pulley, and pulley is connected to this body. It is 0.01 kg. This is the liquid film. Now see, the lower portion of the liquid film is connected, or basically this is in contact with the table. The table is at rest. So the molecules of the liquid film which are in contact with the table are at rest. So the velocity of this lowermost portion is zero. This lower portion of the table is at rest, its velocity is zero. But if I consider this upper portion, this upper portion is in contact with the plate, and the plate is moving with some velocity of 0.085 meter per second. So velocity of the upper portion of the plate is 0.085 meter per second. So this is the velocity of the top portion of the layer, upper portion of the layer, and the velocity of the lower portion of the layer is 0. The thickness of the layer is given. Its thickness is this. This is the thickness of the layer. And this plate is moving with a uniform velocity. It's connected, right, with a constant speed. If it is moving with a constant speed, that means acceleration is 0. If it is moving with a constant speed, that means acceleration is 0. So if I draw the FBD, of 0.01 kg mass, then two forces are acting over it. One is tension, another is its weight, 0.01 g, and the acceleration is 0. So you can simply write both the forces would balance each other. Only acceleration is 0. So if I substitute its values, 0.01 into g is 10, then this comes out to be 0.1. So the tension which is acting over the string is 0.1 Newton. Okay, after tension in the string, now we can come to this plate. The various forces acting on the plate along x-axis is one is tension. Is there any other force which is acting over the plate along x-axis, positive or negative x-axis? Any other force which is acting over the plate?
Friction force.
Yeah, which friction? Viscosity, right?
Viscosity.
If it is moving to the right hand side, then the viscosity will act to the left hand side. That is the friction which is acting. This plate is moving with a constant velocity. Because if it is moving with a constant velocity and this plate is connected through a string, then this too will move with a constant velocity. They will move with the same velocity, right? So if the velocity is constant, now let's solve the plate. For plate, velocity is constant. Velocity constant means the two forces acting along x-axis should balance each other. Velocity is constant, that means acceleration of the plate is 0. If I draw the FBD of the plate, then the FBD of the plate is like, this is the plate. No, this is the plate. One force of tension is acting to the right hand side. Another viscous force is acting to the left hand side. And it's moving with a 0 acceleration. 0 acceleration means tension will balance this viscous force. Tension, we know that tension is this 0.1 Newton. And we know the formula of viscous force, eta A dV over dx. I call this as my first equation. Now let's substitute the values. A is given. The area of the plate is given. See, the area of plate is equal to the area of layer which is in contact with the plate. Only this much portion of the liquid layer is exacting force over the plate. So the area of this much portion is equal to how much is the area? Area is this 0.1 meter square. So this area is 0.1 meter square. Change in velocity with respect to position is, change in velocity is this, change in velocity is this. The difference between the velocity and the bottom and the upper portion of the layer is this 0.085. And the separation is actually the thickness of the layer. So dV over dx is 0.085 divided by dx, thickness of the layer, 0.3 mm. It's 0.3 multiplied by 10 raised to the power minus 3. So if I substitute all values here, it comes out to be that 0.1 is eta into A, which is 0.1 into dV over dx, which is 0.085 divided by 0.3 multiplied by 10 raised to the power minus 3. So you can easily calculate your eta from here. This 0.1 will cancel this 0.1. Your eta will be 0.3 into 10 raised to the power minus 3 over 0.085. This much of decapoise. This much of decapoise is the coefficient of viscosity. This much is coefficient of viscosity. Okay, so after this expression of viscosity, the next is Poiseuille's formula. The next is Poiseuille's formula. Poiseuille's formula basically relates rate of flow of fluid through a pipe to the pressure difference of the pipe. See, what do you mean by rate of flow? Rate of flow. In fluid dynamics, rate of flow has same importance as velocity had in mechanics. Rate of flow simply means its volume of liquid flowing per second. Let's say 10 meter cube of liquid flows through a pipe in 1 second and the rate of flow is 10 meter cube. So you can represent rate of flow by Q and you can write this is delta V over delta T, where delta V is the volume of liquid flowing in time delta T. So the volume of liquid that flows through the pipe in delta T time is delta V over delta T. So let's consider a pipe. So this is a pipe. The area of cross section of the pipe is A. Radius of the pipe is R. Length of the pipe is L. Say a liquid is flowing through the pipe in this way. This is the liquid flowing through the pipe. This liquid is exerting a pressure P1 over the pipe. This liquid is exerting a pressure P2 over the pipe. The pressure difference, these pressures are basically exerted by the fluids. So fluid is flowing through the pipe. The portion of the fluid which is out of the pipe will exert a pressure P1. And obviously this liquid will push this liquid in this direction. Similarly, the liquid which have moved out of the pipe will push the liquid which is inside the pipe to the left hand side direction. So what is the pressure difference? Net pressure difference, Fazil?
P2 minus P1.
P2 minus P1. Which pressure should be higher so that the fluid can flow in this way?
P2 should be higher.
P2 is higher, then the liquid will move to the right hand side direction or the left hand side direction?
Left hand side.
Left. But where is the liquid moving?
Right hand.
Right hand side. Which one is greater?
P1.
P1. So I'm just writing this as P1 minus P2, higher minus lower. This is the pressure difference. And eta is the coefficient of viscosity of the liquid which is passing through the pipe. Coefficient of viscosity of the liquid which is passing through the pipe. So Poiseuille's formula simply says according to Poiseuille's formula, the rate of flow of fluid is proportional to, or not proportional, is equal to rate of flow of fluid through the pipe P is pi P R to the power 4 divided by 8 eta L. This is the formula. And instead of P, I should represent it by Q. This is the rate of flow of liquid through the pipe. Now, the derivation of this result is not a part of your syllabus, but you can derive this using dimensional analysis. In dimensional analysis, we did a topic which is derivation of formula. So using derivation of formula, you can derive this result. This result can be easily derived using derivation of formula. But if that question comes, that would be a part of dimensional analysis, not of fluid mechanics. The derivation of this result is not included in fluid mechanics. You need to remember this formula and you can directly solve the variables. So always remember that this P is not the pressure on the one end. This P is the net pressure, which is P1 minus P2. If P2 is 0, then P would be equal to P1. But if P2 is given, then calculate the pressure difference. Okay, so the numerical is this is the radius of first pipe, that's R1. This is the radius of second pipe, which is R2. The length of the first pipe is 100 centimeter and the length of the second pipe is just 50 centimeter. The pressure, this is A and this is P. So the pressure here at this end is PA, which is 80 centimeter of mercury. And the pressure here at end B, the pressure is PB, which is 76 centimeter. And this is the junction. Here the pressure is, let's say the pressure over the junction is P. This is junction, pressure at junction. Now see, these two pipes are connected. There is no source inside the pipe. That means the only source through which liquid can enter in this pipe is through point A. And the point to which the liquid can leave is B. There is no other source or sink here. That means the rate of flow of the liquid is same. Means the volume of liquid entering pipe B or the volume of liquid flowing through pipe A in 1 second is exactly equal to the liquid flowing through pipe B in 1 second. The equation that we will use to solve this numerical is a simple fact that the liquid flowing here to here is equal to the volume of liquid flowing from here to here. In both the pipes, the rate of flow is same. The volume that's entering here is the same, which is volume is here. So you can say rate of flow at point A is equal to rate of flow at point B. This is it. Now you need rate of flow here. The formula of rate of flow is, you can use Poiseuille's formula. It's pi. Now can you tell me what's the pressure difference for pipe A? At here the pressure is PA. At this end pressure is P. What is the pressure difference, Fazil? Because I have to use this formula. This one. Here P is the pressure difference, which is P1 minus P2. What's the pressure difference here? PA is the pressure at end A and this is the pressure at end B. This junction.
PA minus P.
Yeah, so that will be PA minus P. PA should be greater than P, right? This should be a higher pressure. This should be a lower pressure. Then only the liquid will move inwards. So that's pi P R to the power 4. So radius of A to the power 4 divided by 8 eta L, length of pipe A, which is equal to pi P. What's the pressure difference here? Which point should be at high pressure? This junction or this point B?
Junction.
Junction should be at high pressure. So that's P minus pressure at B, radius of B to the power 4 over 8 eta length of P. So this pi will cancel this pi. The same liquid is flowing. That means at both the ends, the coefficient of viscosity is same. Length is given, PA, PB given. Just try to calculate P. And if you look at these equations carefully, you will find that there is no need for sign convention or unit conversion. This is centimeter, this is centimeter, this is millimeter, this is millimeter. Take P and PB in 80 in centimeter of mercury column only. Get the value of P. How much is P here? So I'm just substituting the values. PA, how much is PA? PA is 80. It's minus P. It's R to the power 4. So RA is 0.1. It's 0.1 to the power 4 divided by LA. LA is 100. This is P minus PB. Pressure at point B is 76. RB, it's 0.2 to the power 4 divided by the length of the section B. Section B is 50. So if I cancel them, it's 2. So this is 80 minus P by 2. 0.1 to the power 4 means it's 10 raised to the power minus 4. Similarly here, this is P minus 76. 0.2 to the power 4 means it's 2 to the power 4 into 10 raised to the power minus 4. It gets cancelled out. So if I multiply it here, this is 80 minus P is equal to, I'm multiplying here with this 2. So it's P minus 76. It's 2 to the power 4 multiplied by 2. So 80 minus P, this is 2 to the power 5. So it's 2 to the power 5P minus 76 into 2 to the power 5. And how much is 2 to the power 5? 4, 8,
32.
16, 32. So that's 80 minus P is 32P minus 76 into 32. So I'm taking P value terms on the right hand side. So that's 80 plus 76 into 32 is 32P plus P. So 76 into 32, how much is it? 76 into 32, 76 into 32. So that's 2432 plus 80. So that's 2512. So it's 2512 is 33P. So this P comes out to be, it's 2512 divided by 33. So 2512 divided by 33 is 76.12. 12 centimeter of mercury. So this is it. So remember, whenever you connect two pipes, the rate of flow of liquid will remain same. The liquid which is leaving the first pipe will enter into the second pipe. The velocity can change due to the change in area of cross section of the pipe, but rate of flow will always remain same. How the velocity will change, that we will do in continuity equation of continuity. Okay, so after Poiseuille's formula, the next thing is Stokes law. See, Stokes law also gives a formula to calculate viscous force. One relation to calculate viscous force is this one. This that we have written. It's a very general expression. This is valid for all types of fluids, for all types of cases, everything. But Stokes law will help you to calculate viscous force only in the case of a spherical body. So it will help you to calculate viscous force for spherical body. viscous force for spherical body. So if a spherical body, so this is the fluid and a sphere is moving through the phase. This is the sphere, this sphere is moving through the fluid. Now, when this sphere tries to move through the fluid, then this fluid will try to oppose the motion of the sphere. This fluid will exert viscous force on the sphere. Now, a very natural question arises that viscous force is the force between the two layers of the fluid, not the force between a fluid and a solid body. Then how could this fluid can exert viscous force on the sphere to the sphere, right? This is what happens when you put a body inside a liquid. A layer of liquid gets stick to the body. This layer of fluid is stuck to this body. So around this body you have fluid, and when you place this body inside a fluid, then this fluid will exert a viscous force over this fluid which is attached to the body. This fluid will exert a viscous force to the fluid attached to the body. As a result, this body will experience a viscous force. So this fluid is not directly exerting force over the body. This fluid is exerting viscous force on the fluid which is attached to the body. The body is wet. If you put a body into a liquid, it gets wet. So this fluid is exerting viscous force over this layer of the fluid. Clear, Harshit and Fazil?
Yes, sir.
So the Stokes law says that this viscous force is equal to 6 pi eta rv, where r is the radius of the body, this is the radius of body, v is the velocity of body. And this eta is just the coefficient of viscosity. So the viscous force which is acting over the body is 6 pi eta rv. Its direction is just opposite to the direction of velocity. Okay, using this Stokes law, you can calculate terminal velocity. Okay, just tell me one thing. I will not ask Harshit. Harshit have already done all these things. Fazil, let's take the case of a raindrop. When a raindrop drops from the cloud, what happens to its velocity? Its velocity remains constant. Its velocity decreases at is moved towards the surface of Earth, or its velocity increases. What do you think happened to the velocity of raindrop? This cloud, a raindrop drop from the cloud, it's moving downwards. As it moves downward, what happened to its velocity? It remains constant, it increases or it decreases. If a raindrop is moving through air column, it's not vacuum, there is air column throughout the surface of Earth. So when the raindrops is falling through air column, can you mention two more forces else than gravitational force which are acting on the raindrop, Fazil? The raindrop is falling through air. Can you mention two more forces else than gravity, which are acting?
Viscous force
One viscous force, okay. Another?
and another.
Good. Viscous force is acting. That viscous force you can calculate using Stokes law, right?
Yes, sir.
Another one more force. Two forces. Buoyant force, buoyancy. Whenever you immerse a body inside a fluid, that fluid will exert buoyant force over the body, right? For the
Yes,
case
sir.
of raindrops through air, your raindrops is basically your body, and air is acting like a fluid. So you will definitely have buoyant force. So what happened is, no, let's consider this as a fluid. This is the fluid. This is the fluid. This is fluid. Now, when I say fluid, this could be liquid or this could be gas, anything. And this is the body. This could be a solid body or it could be an water drop through air. So this is the body. When this body starts moving inside the fluid, it will have three forces. One, okay, first of all, I'm telling what is terminal velocity, and then I will explain why this body achieve a terminal velocity. So when you actually drop this body inside the fluid, then initially the velocity of the body is zero. When you drop the body inside the fluid, that means initial velocity of the body is zero. Now, as soon as this body keeps on falling, its velocity keep on increasing. Its velocity will become 10 meter per second. Then its velocity will become 20 meter per second. Then its velocity will become 30 meter per second. Its velocity should increase, like this is 10. Then velocity becomes 20. Then suddenly its velocity becomes constant. It's keep on increasing, then it becomes constant. First, the velocity will increase, and then at a certain velocity, it becomes constant. It keep on falling with the same velocity, constant velocity of 20 meter per second. We will see why it happens, under what condition it happens, but this is what we call the terminal velocity. This constant velocity is what we call terminal velocity. And this is what happened with air, raindrop in air. When the raindrop drops from the cloud, its initial velocity is zero. Now, as it keeps on falling, its velocity increases, then its velocity attain a constant value, and the raindrop falls with that constant velocity. That constant velocity is known as terminal velocity. So, terminal velocity is the constant velocity with which body move in a fluid. So the constant velocity with which the body move in a fluid is known as terminal velocity. If I draw the graph here, first understand the fact that what is terminal velocity, then we will see why body attains a terminal velocity and what are the conditions under which body can attain terminal velocity. This is time, this is velocity. When body drops, its initial velocity is zero. Its velocity keep on increasing. It keep on increasing, and finally it attain a constant value. This constant value is what we call terminal velocity. This is the terminal velocity. V terminal. This is the terminal velocity. The velocity keep on increasing, then it attain a constant value. This is what we call terminal velocity. Now let's see why body attains a terminal velocity. If I say this is the fluid, this is the fluid. This is the fluid. Huh? It could be anything, liquid, gas, anything. This is your body. You drop this body inside the fluid. Then the various forces which are acting over the body are, the one is the weight of the body, which is acting in downwards direction. This is basically which is pulling the body in the downwards direction. But since this body is inside the fluid, so buoyant force will also act. A buoyant force will also act on the body. Now, this fluid may not be an ideal fluid. This will have friction, or it's better to say viscosity. So a viscous force will also be acting on the fluid, on the body. So these are the three forces which are acting on the body: weight, buoyant force, viscous. Now this is pretty clear. Then when buoyant force and viscous force balance weight of the body, then acceleration would be zero and body will move with a constant velocity. Hey, you remember this thing, right? That if acceleration is zero, that doesn't mean that velocity is zero. That means velocity is constant. Body is moving with a constant velocity. Now the thing is, out of these three forces, buoyant force is constant. Once the body is fully immersed, it's a constant force. Weight is a constant thing. But this viscous force depends on the velocity. So initially here, when velocity is increasing, weight cannot be balanced by buoyant force and viscous force. Weight is greater than buoyant force and viscous force. That's why velocity is increasing. But as soon as body attain this velocity of 20 meter per second, its viscous force increases. See Stokes law, viscous force depends on velocity. At 20 meter per second, the viscous force increasing. Now, these two forces together will balance the weight of the body. Once these two forces balance the weight, the velocity becomes constant. So at terminal velocity, when body achieve terminal velocity, at terminal velocity, you can say that weight of the body is the sum of buoyant force plus the viscous force. This is it. When body attains terminal velocity, then buoyant force and viscous force will balance the weight of the body. This is what happens when a body attains terminal velocity. Buoyant force, what is weight? Weight is mg. Buoyant force is weight of liquid displaced, or not just liquid, weight of fluid displaced. Fluid displaced plus viscous force, which is 6 pi eta rv. You can write your weight as the product of volume and density. Volume of the body is 4 by 3 pi r cube. This is the volume multiplied by rho, which is the density of body, multiplied by g. Weight of fluid displaced. Weight of fluid displaced is equal to volume of fluid displaced, which is equal to volume of the body, because body is fully immersed. I'm just using Pascal's Archimedes principle. That weight of fluid displaced is volume of fluid displaced multiplied by g. And how much is the volume of fluid displaced? That is exactly equal to the volume of the body, because your body is fully immersed. So you can write this as volume of fluid displaced is 4 by 3 pi r cube. Density of the fluid multiplied by g plus 6 pi eta rv. You can take these terms to the left hand side. So you can write this as 4 by 3 pi r cube density of body into g minus 4 by 3 pi r cube density of fluid into g is 6 pi, or not 6 pi eta. I need this v. So let's take some common. 4 by 3 is common, pi is common, r cube is common, g is common. We are left with density of body minus density of fluid is 6 pi eta rv. So we can calculate v from this equation, that v is 4 by 3, it's pi r cube g, density of body minus density of fluid divided by its 6 pi eta rv now. Pi will cancel this pi. R will cancel this cube, right? Square. This is 2, 2s are 4, 2, 3s are 6. So I'm left with V is, it's 4 by 9. It's 4 by 9 R square G, density of body minus density of fluid, and there is no V, divided by eta. This is the expression of terminal velocity. So when body will attain terminal velocity? Body will attain terminal velocity when these two forces will balance the weight of the body. And the velocity at which these two forces balance the weight is known as the terminal velocity. What happens if the density of body is greater than the density of fluid? This is the expression of the first discussion. This is the expression of terminal velocity 2 by 9 r square g by eta, its density of body minus its density of fluid. If density of body is greater than density of fluid, that means your terminal velocity is positive. Now, if your terminal velocity is positive, that means body is falling downwards. That simply means body is falling downwards. Body is falling downwards. Second, if density of body is less than the density of the fluid. The example of this thing is water drops in air. So water drop is body, its density is that of water, which is around 1000. And the fluid is air. Density of air is less than that of water. The density of air is 1.29 something for drop in air. If density of body is less than density of fluid, then the terminal velocity is 2 by 9. It's r square g over eta, density of body minus density of fluid. In that case, this term comes out to be negative. Your terminal velocity will be negative. Terminal velocity is negative, that means body move upwards. That means instead of falling downwards, your body will move upwards in the fluid. The example is air bubble in water. In this case, air bubbles is your body and water is the fluid. So in water, the air bubble does not move in downwards direction, they move in upwards direction. See 8 raindrops of radius 1 mm each falling down with a velocity of 5 centimeter per second. So for small drops, I'm writing the formula of terminal velocity. Terminal velocity is, let's say V1. It's 2 by 9. It's R1 square into G. It's rho density of drop minus density of air divided by eta. That's my first equation. For bigger drop, they combine to form a bigger drop. Okay, just tell me which term will change out of these terms. If the same water, only the size of the drop is changing. Which quantity will change out of these? R, G, rho, sigma, eta. Which quantity will change?
R.
Only radius will change. All other terms will remain same. So that is 2 by 9. It's R2 square G rho minus sigma over eta. Because coefficient of viscosity doesn't depend upon the size, it depends upon the nature of material. Similarly, the densities. So just take the ratios V2 over V1. The ratio would be 2 by 9. It's R2 square G. It's rho minus sigma over eta divided by it's 2 by 9. It's R1 square G. It's rho minus sigma by eta. It's 2 by 9 will cancel this 2 by 9. This thing will cancel this thing. This will cancel this. So we are left with it's V2 by V1. It's R2 square by R1 square. So this is my equation number 3. So you have V1 You have R1, you just need R2. So Fazil, how will you calculate R2 from R1? You have anything to calculate R2?
Will equate the volumes. Volume
Volume
of
you can equate, right? Because volumes, 8 small drops combine to form the bigger drop. So you can write that 8 into volume of small drop is equal to volume of bigger drop. Volume of small drop is 4 by 3 pi R1 cube. The volume of big drop is 4 by 3 pi R2 cube. So you can calculate R2 from here. Okay, now just calculate R2 from here, substitute it here and tell me how much is V1, V2. If I equate these two equations, so I have 8 times R1 cube is R2 cube. You can take cube roots on both the sides, you will get 2R1 is actually equal to R2. So if I make all these substitutions, like if I substitute the value of R2 in 3, I call this as equation number 4. Let's substitute 4 in 3. So what you will get, V2 by V1 is R2, which is 2R1 by R. It gets cancelled out. So you get that V2 is 2V1. Right, Fazil?
Yes, sir.
Substitute V1 is 5. So, no, it's not 2. It's 2, na? Just tell me if I'm making any mistake here. So R2, 8, it's 2R, right? Yeah, it's R2 square, na? Sorry. It's square. It's square. So it's 4V1. It's 4 into 5. So V2 is 20 centimeter per second. If I convert this into meter, that's 0.2 meters. The next thing is the type of flow. We have turbulent flow. Okay, I'm just showing you a video before the type of flows. Okay, just write down the name of the topic. Then we will see an animation. You have to study 2 types of flows. One streamline and another is turbulent. 2 types of flows. One streamline and another is turbulent. So what is streamline flow? Streamline is basically an ordered flow of liquid. Streamline is simply an ordered flow of fluid. A flow which follow a definite order. The order means every particle of the fluid follow the path of its preceding particle. Means simple, if a fluid is flowing in this way, in a line with a very small speed, then the flow is streamlined, ordered flow. But if you keep on increasing the speed of the fluid flow, then at some value of speed, this ordered flow becomes turbulent. The best example, I'm just showing you an animation just to clarify this thing. Yeah, this is the fluid. The liquid is filled in this tap and there is this valve through which you can just fix the velocity of the liquid. Now, if the velocity of liquid is small, it's moving at a very small velocity, then this flow of the liquid, see, the molecules of liquid are moving in a straight line. See this. Just to make it visible, he's adding this red color here. Otherwise, the liquid is this of blue color. Just to show that molecules are moving in a straight line, he's adding red color here. The molecules are moving in a straight line. This flow is known as laminar flow or streamline flow, the same thing. But here, as he increase the velocity, the molecules, see here, the zigzag thing, the molecules are moving randomly. Liquid molecules are moving randomly. That can be easily see through this colored thing. You just put this color here, and since liquid molecules are moving randomly, so color is moving randomly. This flow is known as turbulent flow. That's simple definitions. Laminar and streamline are the same flow. If it is moving in a straight line, then the flow is streamline or laminar. If it is moving randomly, then this is turbulent flow. That's the difference between streamline and turbulent flow. So I'm not writing all definitions from streamline and turbulent flow. I'm just telling you the difference between the two types of flows. It's ordered flow, disordered flow. Each liquid molecule follow the path of its preceding particle. Like say, from a point A, a liquid molecule travels and its velocity is this. This is velocity ideally. So, and this is another molecule. This is point B. When it passes through B, its velocity is B. So I'm considering just 2 points, A and B. Infinite number of molecules will pass through this point A, and if the flow is streamlined, then each molecule will have the same velocity VA. First molecule pass with the velocity VA. Second molecule will pass to the point A, then velocity will be VA. Third will pass point A, the velocity will be VA. So each molecule is following the path of its previous molecule. This is a property of streamline flow. Ordered flow. Another important property. Two streamlines, if you have a streamline. Streamline is also the name for the path of a particle in streamline flow. Let's say a particle is moving in streamline flow. The path followed by the particle in streamline flow is also known as streamline. This is the path followed. So if I say this is the streamline for water, and I ask you to calculate the velocity of water over this point, then draw a tangent here. I ask you to calculate the velocity of water at this point. Simply draw a tangent here. This tangent will give you the velocity of water. Two streamlines can never cross each other. Because if they do so, if streamlines cross each other, then at the point of intersection, you can draw two tangents. These two tangents will meet two different directions of velocities at a single point. In streamlines, particles move in a straight path or in a definite ordered path. It cannot have two velocities at a single point. So two streamlines can never cross each other. On the other hand, turbulence means particle can have any zigzag path. This is known as turbulent flow. Energy is not conserved in turbulent flow. So throughout our discussions in fluids, further discussion in fluid, we will stick to streamline flow. If fluid is moving, your fluid is in streamline flow. This is the ordered flow that we will study.